Good afternoon. Welcome to yet another live session for this Introduction to Photonics course. It's been an exciting journey so far. It's almost been 12 weeks since we started. And I know right now all you guys are quite focused on writing the final exam, doing well in that. My best wishes for the same. And there are several questions related to that as well. And I thought I could possibly get on this live session and address all those questions. Before we go to that, though, I would like to just go back and reflect on what we have been through so far. Okay, so this sort of gives you a eagle's eye perspective of what we have learned so far. Okay, so to do that, let me just go back and look at my contents, right? The contents of the course. So this is what we started with. We said there are certain learning objectives for the course. One is to learn the fundamental principles of photonics and light matter interactions. Second is the ability to develop the ability to formulate problems related to photonic structures or processes and analyze them. And finally, understand processes that help to manipulate the fundamental properties of light. So we were addressing these learning objectives through three primary modules. First one we call as the fundamentals of photonics, where we started from a ray optics picture and then slowly progressed towards a wave optic picture, and then on to an electromagnetic picture, and finally we went on to looking at the statistical properties of light. We defined what coherence of light is. We defined what spatial coherence or temporal coherence means. And in that process, we understood that light emission and, of course, its propagation is quite random in nature. And that randomness can only be explained through, or maybe relatively easily explained through consideration of the quantum nature of light, which is considering light as consisting of photons. So then we went on to look at the properties of photons, the photon energy, the probability that a photon exists at a particular location, the photon flux, and so on. And from that point onwards, we went on to look at interaction of light with other material, specifically interaction of photons with atoms. And we found that was actually quite useful in explaining light amplification. And once we did that, we went on to try to understand what semiconductor light sources and detectors were. So we looked at some laser fundamentals, then went on to properties of PN semiconductor junctions, and using those properties, how we can design semiconductor light sources and detectors. And finally, towards the last couple of weeks, we looked at interaction of light with radio frequency waves and acoustic waves. We looked at manipulation of light by its polarization. And then we moved on to considering the nonlinear response of materials to light, specifically when you apply very high fields, as in the case of second order susceptibility, or in the case of high intensity for third order susceptibility related processes. So all along, we had been trying to give you pointers as to how to use this information that we learn through the lectures, how to apply that to develop structures, to design and develop structures. And that actually goes back to our learning objectives that all along we had been trying to develop the ability to formulate problems related to photonic structures and analyze them, right? So that's what we have been doing, and what we can expect moving forward is, just go back to the main screen here, right? So what you can expect as far as the final exam is concerned is to demonstrate an ability to now put together a complete optical system based on all this information that we have gathered. If I remember right, assignment 7 and assignment 10, I designated them as some mini quizzes, which are sort of mimicking what you may see in the final exam. And so from that perspective, you can say the final exam is going to be, you know, similar to that in the sense that we're going to have a set of objective type questions, multiple choice questions, followed by questions where you are asked to design or analyze a structure. And when it comes to those type of questions, those are typically subjective in nature, which means that you know, do that analysis and then put down an answer in fill up the blanks type. So there has been several requests over the past few weeks to make the question paper, the final question paper especially, as purely multiple choice. And as I have told you in the last couple of live interactions I've had, this course is not meant to be just like that. It's supposed to, like we mentioned, the course objectives. It's supposed to teach you to have the ability to analyze structures and design structures and so on, photonic structures. So from that perspective, the subjective type questions are inevitable, and hopefully I have prepared you guys enough to handle such questions, and that's what this assignment 7 and 10 are supposed to be. Like, if you didn't have any of your notes, any of the lectures in front of you, you are directly addressing those questions and trying to answer those questions. How will you perform? I was actually asking you guys to take those assignments in a closed book format so that you can mimic your performance in the final exam. Now, in case you've not done that so far, what I would certainly advise you to do is to go back to those assignments and then try to once again take those, address those questions without looking at any notes or any videos. So that should actually give you a reasonable practice for the final exam. Now, questions about the format of the final exam, the specific configuration of the final exam, whether what you have done in the assignments, whether that is good enough for your preparation. So let me talk about that in a second. So let me just go back and open a new note. Okay, so you can see it. So if you are asked to now design an optical system or analyze an optical system, how we are going to be doing that. So the final exam is going to be something related to this. So if you have an optical system, you clearly would have a light source. Okay, you're going to have a light source, and you're going to have a receiver for light, right? So you're going to basically have a system that has a source and then a receiver, and then you may have other components within that system. So, for example, if you are, say, building a communication system, you may have uh, a component called a modulator. You may have a component called an isolator. You may have a component that does a filtering operation, selects one particular wavelength among other wavelengths, and you may have a certain propagation medium, which could be either free space or it could be within an optical fiber. And there may be certain propagation characteristics as well. For example, you may have a certain attenuation happening in the fiber, certain dispersion happening in the fiber, and the fiber may behave in a nonlinear fashion. When you increase the amount of light that's coupled into the fiber. So you may have all these effects as part of this link. So the question is, how well do you know the properties of the light source? How well do you know the properties of the receiver? How well do you know about light modulators? Whether you know about how an isolator works, you know about propagation in an optical fiber. These are the type of questions that you can expect as far as your final exam is concerned. So each one of these modules by themselves are consistent with what we have discussed in the class, as well as that is in the lectures, as well as what you have dealt with in the assignments. So, as far as dealing with this type of a question is concerned, I hope you are adequately prepared. Now, if you feel that you do not understand something, I would suggest that you go back and try to look through those lecture components and also try to work out those relevant problems. And if you have questions, please do write to us so that we have an opportunity to address those questions as well. So a lot of times I get comments saying that your questions are too difficult, and I am not such a bright student that I can answer such questions and all of that. That really doesn't help me. The reason is, if you say you do not understand a particular aspect of the question, let's say, for example, one of the questions today, that I got through this form, the response form, is that whether the excited state population should be greater than the ground state population, whether that is a necessary condition for lasing action. So that is a very pointed question. If you ask pointed questions like that, then I can address those questions. On the other hand, if you just say, things are just difficult, I'm not able to do anything about it, then there is hardly anything I can do, because that's what the subject is about, the concepts that we talked about in the lectures. If you understand the lectures, then you should not have problems with the assignments, and so on. So, and if you have any particular query, lack of understanding, you should just bring that up so we have an opportunity to address that. So I think I've given you a general perspective of how the final exam is going to be, and this is short of saying these are the questions themselves, right? So I think given you enough hints about how your final exam is going to look like. So if you have any specific questions beyond that, you may feel free to shoot that. But I can assure you that it is not anything that's beyond whatever we have discussed in the lectures, and it's not anything beyond whatever we have encountered through the assignments. Okay, so if you have a decent grasp of those two, I think you do very well in the final exam. So with that, I would like to actually address a couple of questions that came my way. So let me just go back to that. Okay. So one question is how many questions will be there? How to prepare for the exam? I think I've already addressed that part. I said about one part of it, roughly 30% of your final exam is going to be objective type questions, and the rest 70% is going to be subjective type questions. There's another comment that they like the course very much, but they would like to do research. I don't want to address that. I would suggest that person send an email to me separately, and I can address that separately. Then there is a question about assignment 12, the Magenta modulator. If it is, you know, if it is biased at the null point, I think we asked about what should be the frequency. Suppose you have 1 kilohertz as the frequency applied as the modulating frequency. What should be the modulation frequency of the output light? So there was a question on that. So let me just go back and try to address that. So go back and this. Okay. So let's look at this in a little more detail. Now we talk about a Mach-Zehnder modulator, intensity modulator. When we look at the transfer function of the Mach-Zehnder modulator, we are plotting the transmission of the modulator as a function of phase, and you typically have a response like this, right? Where at zero phase you have maximum, and at pi phase you get to a null point, and then that is just alternating, right? As you go to higher values of phase. So the question is, if I am biased at the null point, so if I am biased at this point, and I have a modulation frequency, let me represent this in a different color. So if I have, say, a sinusoidal modulation like this, what is the frequency of my output? Now, when I look at something like this, this is one cycle of my modulating signal. So what do I expect corresponding to that at the output? So let's say it's going to swing to maximum to minimum. And so you start at this point, and so corresponding point is over here. And then you go through one cycle of maximum and then minimum. And then you go to the negative cycle of your modulation, of your modulating signal. And for the negative cycle, if you're biased at the null point, it goes to the other side of the null point, to the left side of the null point. But that also results in a modulation in a similar way. So within one cycle, we actually ended up getting 2 cycles of going to a maximum and coming back to minimum, right? So if my modulation frequency is FM, what you can say is if you're modulating around the null point, that is going to result in a variation of the output signal with the frequency of 2 times FM. Okay, I think that's what we had asked for in question number 2 of assignment 12. Again, these are things that we have already addressed in the solutions, but I am told that the solutions have not been published yet. So for whatever reason, so we will make sure that all those solutions are available to you by tonight, so you can refer to that, and that can help you in your preparations. Okay, so that hopefully addresses that question. And then somebody else who was also pointing out that assignment 6, 11, 12 solutions are not available. Thank you for bringing that to our attention. Now we will actually make sure that those are available before the end of the day. Then there is this other interesting question about the necessary condition for lasing action. So let me go back and address that. So share that. Just want to share this. Yeah. So so let us actually look at just 1 second. So let us look at a typical laser. Let's, for example, take the example of a 3-level laser. So you have the ground state, and then you have a pump that takes a rareth ion to an excited state, from which you could have non-radiative relaxation. And if this is a metastable state, let me just label these states, the population density, let's say it's N1, N2, and N3. If my excited state, which is whose population density is N2, if that state has a relatively long lifetime, then we said you could have stimulated emission from that. That stimulated emission happens with the cross section, emission cross section, which we denote as sigma E. And but the same signal can also get absorbed, that we can call as stimulated absorption, and that stimulated absorption can happen with the absorption cross section that is defined by sigma A. So if you are looking at the rate equation like we did during our regular lectures, you can go back and look at those lectures. If you do that, we define the gain coefficient gamma as N2 sigma E minus N1 sigma A, right? That's basically the difference between the stimulated emission and the stimulated absorption. That is what is giving you this gain coefficient. Okay. Now, under the condition, if sigma E equal to sigma A, then gamma can be written as sigma times N2 minus N1. And in this condition, you cannot have gain unless you have N2 greater than N1. Okay, so if sigma E equal to sigma A, then N2 greater than N1 is a necessary condition for lasing action. On the other hand, if sigma E is greater than sigma A, right, then you could have a condition where N2 is less than N1, but N2 times sigma E minus N1 times sigma A is still positive, right? So in this case, N2 can be less than N1, but you still have gamma is positive, you still have gain, right? So depending upon the relative value of cross section, and mind you, all these cross section values are a function of wavelength. So if you pick a wavelength where your emission cross section is greater than the absorption cross section, under that condition, N2 need not be greater than N1. Okay, to get gain and to achieve lasing action. Okay. And that is what I think we were trying to ask as a question in probably assignment 10, if I remember right. Assignment 10 maybe first question. But that was the thinking as far as the question was concerned. And of course, this is something that I have also addressed in the lectures. I think week 5 or week 6, most likely week 5. If you just go back and look at those lectures, you will see me addressing this in much more detail there. So please go back and refer to that. Okay, now we'll go back to this screen and see if there are any other questions that we have not addressed so far. Pattern of the paper, I think we have already addressed. So somebody mentioning that you cannot remember all the equations. I would want to tell you that something like what we did just now. This is conceptual in nature. This is not something that you're going to have to remember. If you understand the concept, you should be able to, based on that concept, build the necessary equation. On the other hand, let's say excess noise factor of APD. If I have a question which involves excess noise factor of APD, or let's say the relaxation oscillation frequency of laser diode, those are not things that I developed conceptually. So those are things that I just reproduced from somewhere. So if I ask a question related to those, you can be sure that I will provide the necessary equation so that you can, you can use that and solve the problem. Okay. So bottom line is you don't have to remember any equation. Okay. You should, if you followed the lectures, if you understand how we derived some of those things, you should be able to derive them. If I ask you to derive them, I will actually provide you some credit for that as well. So you can just try to go by that, go by the conceptual understanding of the material. You don't have to mug up equations. Certainly, equations that I did not derive myself, you don't have to mug up at all. You can trust that I will provide those equations. Another comment, how is the optimum phase bias of Mach-Zehnder to achieve linear modulation response? That's a good question, Sonali. Let me just go back and address that from the journal. So let's look at this picture now. So where do I get the most linear response if I'm using a Mach-Zehnder modulator? Okay, so if I consider this point over here, okay, where it's actually the linear part of my transfer function, right? For the Mach-Zehnder modulator. So this is actually for the Mach-Zehnder modulator transfer function. If I consider this point, and it's getting a little confusing, so I'm going to use a different color here. So if I consider that point, if I modulate around that point, then that modulation is going to span a certain swing in the transmission, and correspondingly, you're going to have a modulation at the output like that. So effectively, if you have a pi by 2 as your bias point in the modulator, then that's where you expect the linear response from your modulator. So that is typically referred to as biasing in quadrature. So you need to bias the modulator in quadrature to achieve a linear response. Hopefully that answers your question, Kunal. Assignment 12, question 2. The answer for the same is given as 0 hertz. I will go back and look at that, but if you have 1 kilohertz as your modulation frequency, then you should get 2 kilohertz as your output modulation frequency. So you can actually look at the detailed solution for that. So so we'll clarify that through the detailed solutions. Okay. So I don't see any other questions at this point. So let me stop here. And like I said, the final exam, I do recognize that you feel a little nervous about it, and that nervous energy is not altogether bad. It could actually work out your advantage that you are not complacent and you're doing your best to prepare. But if at this point you can go back and answer any of those questions in the assignments, in any of the assignments, without referring the book, then I would say that you are reasonably well prepared to handle the final exam, and you should do well. And I wish you do well, and I wish you take the knowledge that you gathered from this course to other more advanced courses in photonics, like fiber optic communication technology, integrated optics, biophotonics, and so on. And hope you learn more and you become an expert in this area of photonics. Okay. So with that, let me close this session and thank you all for those of you that tuned in, those of you that are watching this at a later time, and thank you all for participating in this course. Bye now.